As we know that we are building more and more systems that rely on computer systems. So you have to design things that can support medical devices, journal infrastructure, and also airplanes. So all walks of our life are nowadays connected through some kind of computer systems. So what we are doing in this class is we are imparting students with the basic knowledge of how to actually build these things. So what happens before this class, at least at Virginia Tech, is that students are learning about little components, but they have not yet seen how those components will come together to design real big systems that can actually support useful applications. So in this particular class, we have students design those components, put them together into bigger systems. For example, memory management. So as we do big data and as most of our applications become more data intensive, it becomes more important for us to design better memory systems so that we can do more and more with the same hardware. So in this particular class, what they're learning is how do I design very strong, robust, and scalable systems that can support such applications. We have been looking at how variance or performance variance in large-scale computing systems affect overall system performance. So imagine if you have hundreds of computers working together, but 10 of them are slow. So then the entire system may become bottlenecked, may start behaving slow. So we have to figure out a way that all these systems behave more or less the same. So in this particular class, then we added a module that will allow students to explore this variance in the context of different projects they have done. So for example, they have completed a project on memory management. So then we asked the students to say, how about you try different processors? How about you see what will happen if you take the same program and you use one kind of processor and run it again and again, and will it behave the same way? Or we start running it on a different hardware and see what will happen there. So this lets the student understand that perhaps using one kind of hardware may be better in terms of having more stable solution. So far what the students learn without the impact of variance is that they start equating highest performance with success. So they feel like if the thing works the fastest, then it's the best. But what we want to do is we want to correct that vision, and we want to make sure that they understand that it's not performance or fastest that is important all the time. It's also the stability. And one of the reasons for that stability is like the example I gave you, that if you have lots of computers and not all of them work within a certain window, it's not going to be feasible to just keep buying the fastest machines. In fact, what we have learned in some of our research is that going faster can sometimes create variances and interactions that can eventually end up reducing overall time to solution. And time to solution is what you and I as a scientist would care about, or even as a user, because if we want to use an application, we don't care. As a user, we don't care like what's happening behind the scenes. We care, will it always work the same way? Whether it's a phone call, whether it's a network device, whether it's downloading a website or watching a video experience, many of those things are tied to what we call service level agreements or quality of service. And variance is very important to understand, because how the underlying systems will vary can affect what kind of end user experience we can generate from the computer systems.